Good morning, all of you. Today I am going to make an audio recording for visual impaired students of organic chemistry book of Dr. J.M. Segal, modern book. Name of the chapter is Mechanism of Organic Reactions. 3.1 Interaction. During the study of organic chemistry, we come across numerous reactions which the organic compounds undergo. As we study this reaction, we not only want to know which reactants gives rise to which product, but we are also interested in knowing how it happens. Do the reactants change directly into products in a single step, or does the reactions take place by several steps through the formation of reactivity intermediates? The complete description of how a particular reactions take place is called mechanism of the reaction. It tells us which bonds are broken and in what order, and which bonds are formed and in what order. It also tells us about the kinds of intermediates are involved and what are the relative rates of different steps. We shall now consider some important notions and basic concepts involved in the study of organic reactions and their mechanism. 3.2 Important notions. Reactions of organic compounds involves the breaking and making of covalent bond and the movement of electrons from one side to another. To indicate these changes, certain notions involving the use of different kinds of arrows has been adopted as described below. 3.2.1 Curved arrow notion. It is a very useful notion in which a curved arrow indicates the movement of electrons as bond in reactants are broken and new bonds in products are formed. It means that an electron pair moves from the atom at the tail of the arrow of the atom at the head of the arrow. It is illustrated below with the help of reactions between water and hydrogen chloride. HOH plus HCl gives HOH H O positive and plus Cl negative. The electron pair moves from O of H2O to H of HCl. The bond between H and Cl breaks and the electron pair moves to Cl. The electron pair that moves from O forms a new bond with H to gives H3O positive, and the electron pair of HCl bond does goes to Cl to form Cl negative ion. Similarly, reactions between acetylene and amide ion NH2 negative to form acetylide ion CH triple bond C negative and ammonia may be shown as follows. NH2 negative plus CH triple bond CH gives NH3 plus C negative triple bond CH. 3.2.2 Half-headed arrow. As as we will be described in Sec 2.3, sometimes a bond between two atoms breaks in such a manner that each atom gets an electron of the shared pair. To represent this type of symmetrical bond breaking and bond making, half-headed arrows are used as shown ahead. A two electrons B or A bond B gives A plus B. Cl or Cl bond Cl gives Cl plus Cl. CH4 plus Cl gives CH3 radical plus HCl. It may be noted that a half-headed arrow is used for showing the movements of single electrons, while a full-headed arrow is used for a pair of electrons. 3.2.3 Double-headed arrows. This type of arrows are placed in between the various canonical structures of a substance which exhibit resonance. This is to indicate that the actual structure is a hybrid of these structures which are hypothetical and not real. For example, double-headed arrows are placed between the two major canonical structures of benzene to indicate that the actual structure of benzene lies in between these two structures which do not have any real existence. 3.3 Type of bond cleavage. Reactions of organic compounds almost invariably take place through the breaking and formation of covalent bonds. Depending upon the nature of given organic compounds, the nature of attacking reagent, and the reaction conditions, a bond between two atoms of a molecule may be cleavaged or broken in different ways, producing different types of reactions, intermediates. The different possibilities are illustrated below by considering a covalent bond between two atoms A and B. 3.3.1 Homolytic cleavage or homolytic fusion or homolysis. This involves the breaking of a covalent bond in such a way that each atom separates with one electron of the shared pair. AB homolytic cleavage, A radical plus B radical free radical. This leads to the formation of highly reactive neutral particles containing odd or unpaired electrons and known as free radicals. It may be seen that the homolytic cleavage of bond is shown by using half-headed arrows in pairs. 3.3.2 Heterolytic cleavage or heterolytic fission or heterolysis. This involves the breaking of a bond in such a way that both the electrons of the shared pair are carried away by one of the atom. AB heterolytic cleavage, A negative plus B positive if A is more electronegative than B. AB heterolytic cleavage, A positive plus B negative if B is more electronegative than A. Heterolytic fusions leads to the formation of charged or ionic species, one having a positive charge and the other a negative charge. If both the shared electrons are taken away by A, it would be converted into an anion A negative and B into an anion B positive. On the other hand, if both the shared electrons are retained by B, it would change into an anion B negative, while A would have formed a cation A positive as shown above. Quite often, the ionic species formed by heterolytic fusions bears the positive or negative charge on carbon. Such ionic species are known as carbocations, earlier called carbamine ions or carbonyl ions, according as carbon carrying positive or negative charge. It may be mentioned that if a particular covalent bond can undergo either homolytic cleavage or heterolytic cleavage under different conditions, the bond dissociation energy for homolytic cleavage is considerably different from the heterolytic cleavage. In general, the value for homolysis are low, while they are quite high for heterolysis. For example, the bond dissociation energy for CCl bond in CH3Cl for homolytic and heterolytic cleavage are 351 and 949 kilojoule per mole respectively. Homolytic cleavage CH3Cl gives CH3 radical plus Cl radical. Heterolytic fusion CH3Cl gives CH3 positive plus Cl negative. 3.4 Reaction intermediates. The student is already familiar with the fact that in organic reactions, the starting substance seldom change into the product directly in one step. On the other hand, the reactants first change into intermediate substance called reaction intermediates, while ultimately yield the product. The reaction intermediates are generally very unstable and reactive substance which cannot be even isolated. But when we now briefly deals with the main reaction intermediates which we often come across in organic chemistry. 3.5 Carbocations, earlier called carbamine ions. 3.5.1 What are carbocations? A carbocation is a cation in which the positive charge is carried by a carbon in which has only 6 electrons in its valence shell. For example, CH3 positive and CH3 CH2 positive are simple carbocations known as methyl cation and ethyl cation respectively. A carbocation may be assumed to be fragment for a molecule from which an atom or group singly bonded to a carbon gets removed along with the pair of bonding electrons. For example, if a bromide ion is removed from a molecule of a T-butyl bromide, T-butyl cation would be formed as shown below. CH3C Br on second position to CH3 tertiary butyl bromide gives CH3C positive, CH3CH3 plus Br negative tertiary butyl carbocation. Carbocations are very short-lived and highly reactive species. The reactivity of carbocation is due to their tendency to complete the octet of electron-deficient carbon. As a result, carbocations undergo a variety of reactions. Formation of carbocations. Carbocations can be generated in many different ways. Some of the reactions in which they are formed are given below. First, direct ionization. The carbon halogen bond CX in many organic halides generate carbocations in the presence of a highly polar medium. For example, CH3 3CCl T-butyl chloride gives CH3 thrice C positive plus Cl negative tert butyl cation. CH2 double bond CH single bond CH2 single bond Cl allyl chloride gives CH2 double bond CH2 CH2 positive plus Cl negative allyl cation. This method is of particular importance in the formation of a relatively more stable carbocations. Second, by the protonation of unsaturated compounds. Unsaturated compounds such as alkene, carbonyl compounds, and nitriles furnish carbocations on treatment with proton donation solvents. For example, RCH double bond CH2 plus H positive gives RCH positive CH3. C double bond O plus H positive gives C positive OH. C triple bond N plus H positive gives C positive double bond NH. Third, from compounds containing an atom with lone pair of electrons. When an organic compound having a lone pair of electrons on atom, especially oxygen, is treated with an acid, protonation of this atom takes place. This is followed by the elimination of a simple molecule containing this atom to furnish a carbocation. For example, ROH alcohol plus H positive gives ROH protonation alcohol gives R positive plus H2O carbocation. ROR ether plus H positive gives RO positive. HR gives R positive plus ROH carbocation. Fourth, by the decomposition of diazonium salts. For example, RNH2 gives, in presence of NHO2 minus H2O, gives Rn positive triple bond, and diazonium cation gives R positive plus N2 carbocation. Fifth, by the action of superacid on alkyl fluorides. For example, RF plus SbF5 gives FSO3H R positive plus SbF6 negative. Note, the term superacid is used for some exceptionally strong acidic solutions such as SbF5 plus HF or SbF5 plus FSO3H dissolved in SO2 or SO2ClF. 3.5.3 Structure of carbocations. The positively charged carbon of the carbon cation is in sp2 state of hybridization. The three sp2 hybridized orbitals which lie in the same plane are involved in the formation of three bonds with other atoms. The unhybridized p orbitals remain vacant. Thus, the carbocation has a flat structure as represented on the right hand side. The bond angle around the positively charged carbon is nearly 120 degree each. 3.5.4 Classification of carbocations and their order of stability. Carbocations are classified as primary, secondary, or tertiary according as the carbon bearing the positive charge is primary, secondary, or tertiary in nature. In addition, the methyl ion having only one carbon is regarded as a special case. CH3 positive methyl cation, CH3 CH2 positive ethyl cation primary, CH3 CH positive CH3 isopropyl cation secondary, CH3C positive CH3 CH3 T butyl cation tertiary. It has been established that the order of stability of carbocation is R3C positive tertiary highest, then R2CH positive secondary, then RCH2 positive primary, then CH3 positive methyl. 3.5.5 Explanation of relative stabilities of alkyl carbocations. A basic principle involved in discussing the relative stability of carbocation is that how does a given factor influence the magnitude of positive charge carried by the electron deficient carbon of the carbocation. It is apparent that any factor which tends to disperse the positive charge by distributing it over the rest of the molecule stabilize the carbocation. In contrast, any factor which tends to intensify the positive charge destabilize the carbocation. The relative stabilities of alkyl carbocation as given above can be explained in terms of inductive effect and hyperconjugation in terms of the above principle. First, inductive effect. This is the main factor operating in determining the relative stabilities of carbocation. As if well known, the alkyl group are more electrolyzing than hydrogen. As such, an alkyl group attached to positively charged carbon of a carbocation tends to release electrons towards that carbon due to its plus I effect. In this way, the positive charge on the carbon gets dispersed. This dispersal of the charge stabilizes the carbocation. Now, the more the number of alkyl group, the greater the dispersal of positive charge, and therefore more the stability of carbocation. That is why a tertiary carbocation having three alkyl groups attached to the positive carbon is more stable than a secondary carbocation with two alkyl groups. The secondary ion in turn is more stable than a primary carbocation having only one alkyl group. The methyl carbocation does not have any alkyl group and is therefore the least stable. R3C positive tertiary carbocation maximum dispersal of positive charge, maximum stability. R2CH positive secondary carbocation, RCH2 positive third primary carbocation, CH3 positive fourth methyl carbocation, least dispersal of positive charge, least stable. It is quite evident that presence of electron withdrawing substituent minus I effect which would destabilize the carbocation by intensify the positive charge on carbon. Second, hyperconjugation. The concept of hyperconjugation is also to some extent responsible for the observed order of relative stabilities of carbocation. Hyperconjugation can take place here through the overlap of sigma orbitals of alpha CH bond of alkyl group and the MTP orbitals of carbocation. Taking CH C positive to represent a carbocation in general, delocalization of electrons through sigma p orbital overlap may be shown as. Due to this overlap, the delocalized electrons bind together three atoms, two carbon and one hydrogen to some extent. In terms of resonance, the above situation may be depicted as CH positive gives C double bond C plus H positive. The net result is that in the actual structure, CH bond is slightly lesser than a single bond. The carbon-carbon bond has some double bond character, while the positive charge is partially accommodated by hydrogen atom. This partial accommodation of positive charge over hydrogen leads to dispersal of charge and consequently stabilize the ion. In methyl carbocation, no such dispersal of charge is possible because hyperconjugation does not take place. Second, in ethyl carbocation 1 degree which contains 3 alpha hydrogens, the positive charge can be dispersed over 3 hyperconjugation structures possible in addition to the normal structure as shown below. CH3 CH2 positive CH2 double bond CH2 plus H positive CH double bond CH2 double bond CH2 plus H positive. In isopropyl carbocation 2 degree which contains 6 alpha hydrogens, there will be 6 hyperconjugation structures possible. CH3 CH positive CH3 CH2 double bond CH3 plus H positive plus CH2 double bond CH3 CH2 double bond CH3 plus H positive, etc. In tert-butyl carbocation 3 degree which contains 9 alpha hydrogens, there will be 9 hyperconjugation structures possible. CH3 C positive CH3 H positive CH2 double bond CH3 H positive CH2 double bond CH2 double bond CH3 plus H positive, etc. As the number of contributing structures and with the dispersal of charge becomes more, the stability of carbocation goes on increasing. Thus, the relative stability of alkyl cation may be due to the combination of inductive effect and hyperconjugation, although it is usually explained in terms of inductive effect alone. Third, conjugation of positive charge with a double bond or benzene ring. Resonance stabilization. The carbocation in which the positive charged carbon is conjugated with a double bond or benzene ring have been found to have extra stability. This has been attributed to resonance effect involving the electrons of the double bond. For instance, allyl cation is a resonance hybrid of two equivalent structures as shown below. CH2 double bond CH2 positive CH double bond CH2. It is apparent that positive charge of the carbon of the carbocation gets dispersed over two carbon atoms. Hence, the allyl cation acquires a greater stability and is found to be more stable than simple alkyl cation. Similarly, benzyl carbocation is greatly stabilized by resonance as shown below. CH2 positive benzene, CH2 double bond benzene positive, CH2 double bond benzene positive, CH2 double bond benzene positive, CH2 positive benzene. It is evident that carbocation having more than one phenyl group attached to positively charged carbon would be still more stable. This is because there will be greater dispersal of positive charge due to larger number of contributing structures. Accordingly, diphenyl methyl carbocation benzene CH positive benzene would be more stable than benzyl carbocation. Benzene CH positive benzene CH double bond benzene positive, benzene CH double bond benzene positive, benzene CH double bond benzene positive. Three more contributing structures. Similarly, triphenyl carbocation benzene 3 benzene C positive would be still more stable. Triphenyl carbocation 6 more contributing structures. In fact, triphenyl methyl carbocation is so stable that some of its salts, such as ferrochlorates, can be isolated and stored for months. Effect of substituents on the stability of benzyl carbocation. It can be readily understood that the presence of electron releasing group at the ortho and para positions of the phenyl group with respect to the position where CH2 positive groups is attached, which tends to further stabilize the benzyl carbocation. On the other hand, the presence of electron withdrawing group at these positions would have the positive effect. For example, the order of stability of following substitute benzene ions is CH3O benzene CH2 positive is more benzene CH2 positive than NO2 benzene CH2 positive. CH3O has plus I effect, NO2 has minus I effect. For instability of vinyl and phenyl carbocations, the carbocations in which the positive charge is carried by a doubly bonded carbon atom, such as vinyl cation CH2 double bond CH positive and phenyl cation C6H5 positive, are found to be highly unstable. This is because these ions do not undergo resonance stabilization at all. The resonance for lack of resonance is that the vacant orbitals of the carbon carrying the positive charge is perpendicular to the double bond and therefore it cannot participate in resonance. Determination of relative stabilities of different kinds of carbocations. It is evident from the above discussions that the stability of carbocation is primarily related to the dispersal of the charge carried by the positively charged carbon. The dispersal of charge may be due to inductive effect, hyperconjugative effect, or resonance effect as explained above. The relative stabilities of different kinds of carbocations can be measured in terms of heterolytic bond dissociation energy, leading to the formation of carbocations. AX gives A positive plus X negative. On the basis of these values, the decreasing order of stability of some of the common carbocations are given ahead. CH3 thrice C positive T butyl, then CH2 positive benzyl, isopropyl, allyl, N-propyl, ethyl, vinyl, then phenyl, then methyl, CH3 positive. It may be pointed out, however, the benzyl, isopropyl, and allyl carbocations are almost equally stable. Similarly, vinyl, phenyl, and ethyl carbocations have nearly the same stability. Problem 3.1. Arrange the following carbocations in order of decreasing stabilities. C6H5 CH2 positive, C6H5 thrice C positive, C6H5 C positive, CH3 CH3, C6H5 CH positive, CH3 C6H5 positive. Answer: C6H5 thrice C positive, then C6H5 C positive, CH3 CH3, then C6H5 CH positive, CH3, then C6H5 CH2 positive, then C6H5 positive. Problem 3.2. Which of the following carbocations is the most stable and which is the least stable? CH2 double bond CH single bond CH2 positive, CH3 CH2 CH2 positive, CH2 double bond CH positive. Answer: CH2 double bond CH2 positive is the most stable. CH2 double bond CH positive is the least stable. Problem 3.3. Arrange the following carbocations in order of decreasing stability. Justify your answer. Benzene minus CH2 positive, CH3O benzene CH2 positive, NO2 benzene CH2 positive. Answer: CH3O benzene CH2 positive, benzene CH2 positive, NO2 benzene CH2 positive. 3.5.6. Rearrangements of carbocations 1-2 shifts. An important feature of carbocations is that they can undergo rearrangement reactions to form more stable carbocations. This rearrangement involves the shift of either a hydrogen or alkyl or allyl group along with its electron pair from an adjacent carbon to the positively charged carbon. Such shifts are known as 1-2 shifts. The shift of hydrogen is known as 1-2 hydride shift, while that of alkyl group is known as 1-2 alkyl shift. The cation thus formed contains a new charge center and is more stable than the original carbocation. For example, first 1-2 hydride shift CH3 CH2 positive and propyl cation 1 degree. In presence of 1-2 hydride shift CH3 CH positive CH3 isopropyl cation 2 degree more stable. Second, 1-2 methyl shift CH3C CH3 CH3 CH2 positive neopentyl cation 1 degree. In presence of 1-2 methyl shift CH3C CH2 CH3 second CH3 and C positive 2 methyl 2 butyl carbocation 3 degree more stable. The rearrangement reactions of carbocations are discussed in details at earlier stage in the book. 3.6 Carboanions. 3.6.1 What are carboanions? A carbanion is an anion in which the negative charge is carried by a carbon. This carbon has 3 bonds with one or more other atoms and possesses a lone pair of electrons. For example, C negative triple bond CH is a simple carbanion known as acetylide ion. A carbanion may be assumed to be a fragment of a molecule when one of the atoms or group of singly bond to an carbon is removed without the bond pair of electrons. For instance, removal of an hydrogen of methyl part of acetaldehyde molecule as a hydrogen ion results in the formation of carbanion as shown below. Acetaldehyde OH negative plus CH3 CHO gives CH2 negative CHO plus H2O carbanion. Carbanions constitute a highly unstable and one of most reactive reactions intermediates in organic chemistry. They are very frequently involved in the reactions of aldehyde, ketone, ester, etc. The reactivity is due to the fact that the negatively charged carbon in them has got a lone pair of electrons. It has a strong tendency to donate this space to some electron deficient species. Therefore, carbon ions easily participate in many reactions. 3.6.2 Formation of carbon ions. There are two main methods by which carbon ions are generated as given below. First, by the dissociation of a molecules in which an atom or group singly attached to carbon leaves it without the electron pair, that is CH gives C negative plus H positive. In most of the case, the leaving group is a proton and having a base is required to facilitate the process. Thus, the formation of a carbon ion is an acid-base reaction. CH plus B negative base gives C negative plus BH. Since the presence of electron attracting substituents such as carbonyl, cyano, or nitro groups on the carbon carrying the hydrogens makes the hydrogen relatively more acidic and therefore more easily removable as a proton. The generation of carbon ions from such compounds plays a very important role in organic reactions. For example, OH negative plus CH3 COHO gives CH2 negative CHO plus H2O. C2H5O negative plus HCH2 NO2 gives CH2 negative NO2 plus C2H5OH. To remove a proton from a hydrocarbon, very weak acid, very strong base such as soda amide in liquid ammonia has to be used. For example, CH double bond CH plus NH2 gives liquid NH3, CH triple bond C plus NH3. But aromatic compounds of the type triphenyl methyl generate carbon ions very easily in the presence of a base. C6H5 3CH plus OH negative triphenyl methane gives C6H5 3C negative triphenyl methyl anion plus H2O. It may be pointed out that apart from protons, other living groups are also known to lead to the formation of carbon ions. For example, RCO2 negative gives R negative plus CO2. Second, by the addition of a nucleophile to carbon-carbon multiple bond, C double bond C plus Nu nucleophile gives C negative C nucleophile. But this type of addition occurs only when the double bond is activated towards nucleophilic attack by electron withdrawing group such as carbonyl, cyano and nitro groups. For example, C2H5O negative plus CH2 double bond CH triple bond N gives C2H5O CH2 CH negative C triple bond N. 3.6.3 Structures of carbon ions. The negatively charged carbon of carbon ions is in a state of sp3 hybridization, so that the hybridization orbitals are directed towards the corners of a tetrahedron. Three of the hybridized orbitals are involved in the formation of single bonds with other atoms, while the fourth orbital contains a lone pair of electrons. Thus, carbon ions has distorted tetrahedral or pyramidal structures as shown on the right hand side, but the bond angles around negatively charged carbons are less than 109 degree 28 minute. This is because lone pair bond pair repulsion is greater than bond pair repulsion. It must be pointed, however, in case of carbon ions in which negatively charged carbon having the lone pair of electrons is in conjugation with the multiple bond, the carbon ion has a planar structure. Some common examples of carbon ions having planar structures are given below. Al- Allyl carbon ion CH2 double bond CH2 negative. Benzyl carbon ion CH2 negative CHO acetic aldehyde carbon ion. 3.6.4 Classification of carbon ions and their order of stability. Like carbocations, carbon anions are also classified as primary, secondary, and tertiary carbon ions according as the negatively charged is carried by a primary, secondary, or tertiary carbon. In addition, methyl carbon ion is considered to be a special case. Thus, we have CH3 negative methyl carbon ion, CH3CH2 negative ethyl carbon ion primary, CH3CH negative CH3 isopropyl carbon ion secondary, CH3C negative CH3CH3 tert butyl carbon ion tertiary. The order of stability of different classes of carbon ion has been found to be CH3 negative methyl, then RCH2 negative primary, R2CH negative secondary, then R3C negative tertiary. 3.6.5 Explanation of relative stabilities of carbon ions. First, inductive effect. The above order of stability of primary, secondary, and tertiary carbon ions can be justified on the basis of electron releasing plus I inductive effect of alkyl group. Due to this effect, the alkyl group tends to increase the electron density on the negative charged carbon. As a result, the carbon ions becomes less stable and more reactive towards electron deficient species. Now, the greater the number of alkyl groups in the carbon ions, the more would be its reactivity and the lesser its stability. This is in keeping with the order of stabilities given above. It is evident that the presence of electron withdrawing substituent minus I effect such as NO2, C triple bond and etc. will stabilize the carbanion by dispersing the negative charge on carbon. For example, NO2 benzene CH2 negative p-nitrobenzyl carbanion is more stable than benzene CH2 negative due to the presence of electron withdrawing NO2 group. On the other hand, presence of groups having plus I effect such as R, RO, OH, etc. will destabilize the carbon ion by intensifying the negative charge. Second, hybridization. The relative stabilities of some carbon ions can also be compared in terms of hybridization. For example, let us consider the following carbon ions: RC triple bond C alkyl carbanion sp 50% S character, RCH double bond CH alkyl carbanion sp 2 33% S character, RCH2CH2 alkyl carbanion sp3 25 S character. State of hybridization of negative charged carbon and percentage of S character. It may be noted that hybridized orbitals having greater S character has a relatively more electron attracting tendency or electronegativity than orbitals having lesser S character. At the same time, the greater the electronegativity of an atom, it can accommodate a negative charge more easily. Therefore, the negatively charged carbon of alkyl ion can accommodate a negative charge more easily, and therefore the alkyl ion is more stable than alkyl ion, which in turn is more stable than alkyl ion. Third, resonance or conjugation. As in case of carbocations, even the carbanions which exhibit resonance or conjugation have extra stability due to the dispersal of negative charge as shown below by allyl carbanions. CH2 double bond CH, CH2 negative, CH2 negative, CH double bond CH2. Similarly, benzyl carbanion is highly stabilized by resonance. It is evident that the more the number of phenyl groups attached to the carbon carrying the negative charge, greater will be the dispersal of negative charge due to large number of contributing structures. That is why diphenyl methyl carbanion is more stable than benzene carbanion. 3 more contributing structures. For the same reason, triphenyl methyl carbanion is one of the most stable carbanion. 6 more contributing structures. The carbanion obtained by removal of alpha hydrogens from carbonyl compounds are also stabilized by resonance as shown below. CH2 negative, CHO, CH2 double bond, CHO negative. 3.7 Free radicals. 3.7.1 What are free radicals? A free radicals is an atom or group of atoms having an odd or unpaired electrons. It is denoted by putting a dot against the symbol of the atom or group of atoms. For example, Cl dot stands for a chlorine free radicals, while CH3 dot denotes a methyl free radical. Free radicals are electrically neutral species which are usually formed by the homolytic cleavage of molecules in reactions takes place in gas phase or in non-polar solvents. For example, ClCl gives 2Cl dot chlorine free radicals. C6H5 C double bond O O O C double bond O C6H5 benzoyl peroxide gives 2C6H5 C double bond O O dot benzol like free radical. Due to the presence of odd electrons, free radicals are paramagnetic in nature. Free radicals are highly short-lived species. They are extremely reactive, and as soon as they are formed, they immediately participate in some further reactions. The greater reactivity is due to the tendency of the odd electrons in them to get paired up. 3.7.2 Formation of free radicals. There are two main methods by which free radicals are usually formed. First, by thermal or photochemical homolysis of a covalent bond. For example, CH3 4 Pb tetramethyl lead in presence of heat gives Pb plus 4CH3 dot methyl free radical. C6H5CO C double bond O C double bond O C6H5 benzyl peroxide heat 2C6H5COO dot benzoic free radical gives 2C6H5 radical phenyl free radical plus 2CO2. CH3CO CH3 diacetyl in presence of heat gives 2CH3CO dot acetyl free radical. Second, by oxidation reduction reactions involves gain or loss of a single electron. For example, ROO negative gives ROCOO dot gives R dot plus CO2. 3.7.3 Structure of free radicals. It may be pointed out that in case of free radicals containing carbon, the state of hybridization of carbon atoms having odd electrons is not clearly established. However, there is a strong evidence to indicate that most of the alkyl free radicals, such as methyl radicals, are actually planar. This means that the carbon atoms carrying the odd electrons is in sp2 hybridized state. The three coplanar hybridized orbitals are involved in the formation of three single bonds with other atoms. The unhybridized p orbitals, which lies in a plane at right angle to the plane of hybridized orbitals, carries the odd electrons. The bond angle around the carbon carrying the odd electrons is approximately 120 degree each. 3.7.4 Classification of free radicals and their order of stability. Alkyl free radicals are classified as primary, secondary, or tertiary according as the odd electrons is carried by a primary, secondary, and tertiary carbon atoms. But methyl free radical CH3 dot having only one carbon is treated as a special case. Thus, we have CH3 dot methyl free radical, CH3 CH2 dot ethyl free radical primary, CH3 CH dot CH3 isopropyl free radical secondary, CH3 C dot tert butyl free radical tertiary. The order of stability of different types of free radicals relatively to the alkane from which they are derived is found to be tertiary, then secondary, then primary, then methyl. This order is derived from the bond dissociation energy involved in their formation. The lesser the bond dissociation energy in the formation of free radical, the more is its stability. To illustrate the above statement, let us consider the homolytic fusions of an alkane into an alkyl radical and a hydrogen atoms, that is RH gives R dot plus H dot. It is apparent that the delta H of such a dissociation process must be equal to the bond dissociation energy of the bond between the concerned hydrogen and the carbon of the alkyl group. A study of delta H of several reactions involving the dissociation of different alkanes to form different classes of alkyl radicals showed that the amount of energy required to form various classes of alkyl radicals are in order: methyl, then primary, then secondary, then tertiary. If more energy is required to form one radical than the other, it means that relative to the alkanes from which it is formed, the radical contains more energy than the other and is hence less stable. Thus, it may be concluded that relative to the parent alkane, in each case the order of stability of free radicals is tertiary, secondary, primary, methyl. It must be emphasized that this order is based only on the difference in energy between the alkyl radicals and the parent alkane in each case. As such, it does not reflect the order of absolute stabilities of the individual radicals. To make this point clear, let us consider the case of methyl radical and ethyl radical, which is the simplest primary radical. The difference in energy between methane and methyl radical delta H for the reaction CH3H gives CH3 dot plus H dot being 433 kilojoule is more than the difference between ethane and ethyl radical delta H for the reaction CH3CH2H gives CH3CH2 dot plus H dot being 410 kilojoule. This merely means that the stability of methyl radical relative to methane is lesser than the stability of ethyl radical relative to ethane. 3.7.5 Explanation of relative stability of alkyl free radicals. First, hyperconjugation. The relative stabilities of alkyl free radical are explained primarily in terms of a concept of hyperconjugation. With the exception of methyl free radical, all other alkyl free radicals undergoes Hyperconjugation through overlap between sigma orbitals of hyperconjugations through overlap between sigma orbitals of hyperconjugation through between and sigma orbitals of alkyl groups and p orbitals containing the odd electrons taking CH C dot to represent an alkyl free radical. In general, delocalizations through sigma p orbitals overlap may be shown as in the adjacent figure. As a result of this overlap, the delocalized electrons helped in binding together three atoms, two carbon and one hydrogen to some extent. In terms of resonance, the above situation may be represented by saying that the given alkyl free radicals is a resonance hybrid of two contributing structures as shown below. CH dot C plus H dot. This means that CH bond is slightly less than a single bond, while C bond has some double bond character and the odd electron is partially present on hydrogen atom. The actual number of contributing structures or the extent of delocalization of odd electrons depends upon the nature of alkyl radicals. The more the number of contributing structures, or the more extensive the delocalization, the more stable is the radical. Let us, for instance, compare the relative stabilities of methyl and ethyl radicals. In methyl radical, hyperconjugation is not possible and no delocalization of odd electrons takes place, but in ethyl radical 1 degree there is considerably delocalization of odd electrons due to contributing from normal structures and three hyperconjugation structures as shown below. CH3CH dot, then CH2 plus H dot CH2 dot H CH2 plus H dot. As a result of stabilization due to resonance or delocalization, ethyl radical is about 25 kJ per mole more stable than methyl radical. As we pass on to isopropyl radical 2 degree, it will have 6 hyperconjugation contributing structures in addition to the normal structures as given below. And due to greater delocalization resulting from more contributing structures, isopropyl free radical is more stable than methyl free radical to the extent of 37.6 kJ per mole. Similarly, tert-butyl radical 3 degrees stabilized to the extent of 50 kJ per mole, since it has 9 hyperconjugation structures in addition of the usual structures, and therefore very extensive delocalized of electrons takes place. In general, the order of stabilities of alkyl radical is tertiary, then secondary, then primary, then CH3 radical. Second, resonance or conjugation, like carbocations or carbon ions free radical exhibit resonance or conjugation are also more stable than simple alkyl radicals. For example, allyl free radical is more stable than alkyl free radical because the former is stabilized by resonance. CH2 double bond CH single bond CH2 double bond CH double bond CH2. Similarly, benzyl free radicals is highly stabilized by resonance. It can be readily understood that triphenyl methyl free radical C3 benzene dot is very highly stabilized by resonance due to presence of three phenyl groups attached to the carbon carrying the odd electron. Determination of stability of some common free radicals of different kinds. The relative stabilities of free radicals can be measured by determining homolytic bond dissociation energy of RH bond. The relative stabilities of some common free radicals are given below in decreasing order. CH2 double bond CH2 radical, then CH3 thrice C radical, CH3 twice CH radical, CH3 dot CH2, then CH3 dot, then CH2 double bond CH dot, then benzene dot, then phenyl CH2 dot. 3.8 Carbenes. 3.8.1 What are carbenes? Carbenes are neutral divalent chemical species in which our carbon is covalently bonded to two atoms and have got two non-bonding orbitals having two electrons between them. In other words, carbene contain a neutral carbon atom having 6 electrons in the valence shell, out of which 2 are shared. The most common carbenes are CH2 methylene and CCl2 dichloromethylene. Carbene are a highly reactive species having a very short life period. 3.8.2 Types of carbenes. An interesting feature of carbene structure is that it may exist in two distinct states. First, singlet carbenes. These are carbenes in which unpaired electrons are paired, that is, they are present in different orbitals. Second, triplet carbenes. These are carbenes in which unshared electrons are not paired, that is, they are present in different orbitals. For example, methylene carbene can have either of the following two structures depending upon its mode of formation: CH2 singlet methylene unshared electron paired, CH2 triplet methylene unshared electrons are not paired. Triplet carbenes represent biradicals, that is, divalent free radicals. 3.8.2 Formation of carbenes. There are two methods generally employed for the generation of carbenes. First, by the thermal or photochemical decomposition of aliphatic diazo compounds, ketenes or cyclopropenes or oxiranes. For example, dimethene CH2N2 in presence of it gives CH2 plus N2 methylene carbene. CH2 double bond C double bond O ketene in presence of it gives CH2 plus CO. C6H5 CH CH2 phenyl cyclopropane or phenyl oxirane in presence of heat gives CH2 plus C6H5CH double bond CH2. Second, by the action of a base on suitable halogen compounds. So this method is usually employed for the generation of halogen carbenes, and the base commonly used is potassium tert butoxide, for example, chloroform. CHCl3 plus CH3 thrice CO negative tert butoxide ion gives C negative Cl3 plus CH3 thrice COH gives Cl2 plus Cl negative. It may be noted that in the above reaction, H positive and Cl negative are removed from the same carbon, that is, alpha elimination takes place. A well-known example of a reaction in which carbene is formed as an intermediate is Raman-Timmer reactions of phenol to give salicylic aldehyde. It involves the formation of dichlorocarbene CCl2 as an intermediate. Phenol plus CHCl3 plus 3COH gives phenol CHO. Salicylic aldehyde plus 3KCl plus 2H2O. 3.8.4 Structure of carbenes. In singlet carbenes, the central carbon is in state of sp2 hybridization of the 3sp2 hybrid orbitals. Two are used in the formation of two single bonds with the monovalent atoms or groups attached to carbon. The third sp2 orbitals contains the unshared pair of electrons, while the unhybridized p orbitals is empty. In triplet carbenes, the central carbon is in the state of sp hybridization. The two sp hybridized orbitals are used in the forming a single bonds with the two monovalent atoms or group attached to the carbon. The two unhybridized p orbitals contains one unshared electron each. 3.8.5 Relative stabilities of carbenes and its explanation. It has been found that triplet carbenes are lower in energy and therefore more stable than singlet carbenes. This is because the placement of two electrons in a single orbital in singlet methylene involves electron repulsion energy which must be overcome to pair the two electrons in the same orbitals. On the other hand, in triplet carbenes, the two electrons occupy different orbitals and the electron repulsion is much less. As a result, singlet methylenes have higher energy than triplet methylenes. The difference in energy is about 37.6 to 46 kilojoule per mole. 3.6.6 3.8.6 Comparison of singlet and triplet carbenes. Singlet carbenes in this two unshared electrons are present as a pair in one orbitals. This is relatively less stable. The central carbon is sp2 hybridized. Triplet carbenes in this the two unshared electrons are present as two unpaired electrons in different orbitals and thus is represented as biradical. This is relatively more stable. The central carbon is sp hybridized. 3.9 Nature of reagents. When two substances react together, one of the substances is regarded as the attacking reagent while the other is taken as a substrate, that is the substance which get attacked. The new substance formed as a result of the reaction are called products. Thus, the occurrence of a chemical reactions may be depicted as substrate plus attacking reagents give products. It may be pointed out that the term attacking reagent is usually employed for the substance whose presence brings about a chemical change in the given substance, that is substrate, to form the product. But the use of the two terms is purely relative. A particular substance may be termed as a substrate in one reaction and an attacking reagent in other. However, the following conventions are generally followed in the use of the two terms. First, in a reaction between an organic and an inorganic substance, the organic substance is treated as the substrate while the inorganic substance is taken as the attacking reagent. For example, C2H5 iodoethane substrate plus aqueous KOH attacking reagents gives C2H5OH plus Ki. Second, in a reaction between two organic substances, the substance which supplies the carbon atom in the formation of a new bond between carbon atom and an hetero atom is treated as a substrate. The other substance is taken as the attacking reagent. For example, CH3COOH ethoic acid substrate plus OHC2H5 ethanol attacking reagent gives CH3COOC2H5 a new bond formed. Third, in a reaction between two organic substances involve the formation of a carbon-carbon bond, one of the substances is attributably assumed to be substrate while the other is taken as the attacking reagent. For example, benzene substrate plus COCl CH3 ethanolic chloride attacking reagents gives benzene, COCH3 plus HCl. 3.9.1 Classification of reagents. There are three types of attacking reagents taking place in organic reactions. These are: first, free radicals. Their formation are relatively reactivity has already been discussed. Second, electrophilic reagents. An electrophilic reagents or an electrophile, that is electron loving particles, is a reagent containing an atom which is deficient in electrons. Because of the presence of electron deficient atom, such a reagent tries to seek electrons from other source and thus behaves as a Lewis acid. It attacks some molecules at a point of high electron density. Types of electrophiles. There are two types of electrophiles. First, positively charged ions or positive electrophiles. Positively charged ions such as hydrogen ions H positive, hydronium ion H3O positive, chlorinium ion Cl negative, nitronium ion NO2 positive plus carbocations act as nucleophilic reagents. Second, neutral electrophiles. These are electrophile reagents in which the electron deficient amount does not carry any charge. For example, AlCl3, FeCl3, BF3 belongs to this category. There are certain substances in which the central atom has a complete octet of electrons and still it has a tendency to coordinate more electrons due to the presence of empty d orbitals. SnCl4 affords an example of such an electrophile. Carbene act as an electrophiles because the carbon in them has only 6 electrons rather than an octet. Reaction involving electrophilic reagents are known as electrophilic reagents. Third, nucleophilic reagents are nucleophilic reagents or a nucleophile, that is nucleus loving particles, is a reagent containing an atom having an unshared or lone pair of valence electrons. Because of this free pair of electrons, such as a reagent is in search of a site which with which to share electrons and in the same way behaves as a base. Lewis concept of bases. It attacks molecules at a point of a low electron density. For example, consider an OH ion. The oxygen present in the ion contains unshared pairs of electrons. Due to this reason, OH ions attack some molecules containing a center of low electron density so as to share the electrons at that point. Types of nucleophiles. Nucleophiles are also of two types. First, negative nucleophiles or negatively charged ions. All negatively charged ions such as hydroxyl ions, OH negative halide ions, X negative alkoxide ions, R negative cyanide ions, Cn negative, and carbon ions act as a nucleophilic reagent. Second, neutral nucleophiles. These are nucleophile reagents which contains atoms with lone pair of electrons but do not carry any charge. Water H2O, ammonia NH3, and alcohols ROH are neutral nucleophiles. Reactions involving nucleophilic reagents are known as nucleophilic reactions. To be precise, all electrophilics and nucleophilic should be capable of forming covalent bonds when they participate in a reaction. For this reason, positive ions such as sodium ions and Na positive having noble gas configuration are not treated as electrophiles because they cannot form covalent bonds as they already having noble gas configuration. 3.10 Classification of organic reactions. The organic reactions may be broadly classified into the following categories. These are: first, substitution or displacement reactions; second, addition reactions; third, elimination reactions; fourth, rearrangement reactions; fifth, isomerization reactions; Sixth, condensation reactions. Fourth, molecular reactions. 3.10.1 Substitution reaction. A substitution reaction is that which involves the direct replacement of hydrogen atom or some other groups of molecules by some other atoms or group without any change in the structure of remaining parts of the molecules. The product obtained is known as substitution product, and the new atom or group which enters the molecule is known as substituent. For example, when chlorine reacts with methane in the presence of diffuse sunlight, the hydrogen atoms are replaced by chlorine atoms one after the other, leading to the formation of the substitution product. CH4 plus Cl2 gives CH3Cl methyl chloride plus HCl. Similarly, the reaction of a methyl iodide with an aqueous solution of potassium hydroxide to form methyl alcohol is a substitution reaction. CH3I plus KOH methyl iodide aqueous gives CH3OH methyl alcohol plus Ki. Substitution reactions may involve free radicals, electrophilic or nucleophilic reagents. Accordingly, they are subdivided as: first, free radical substitution reactions. For example, halogenation of alkenes is a free radical substitution reaction. Cl gives 2Cl dot, CH3H gives plus Cl dot gives CH3 dot plus HCl, CH3 dot plus Cl gives CH3Cl, chloromethane plus Cl dot, and so on. Second, electrophilic substitution reactions. Nitration and sulfonation of benzene are important examples of electrophilic substitution reaction. Benzene plus NO2 positive nitronium ion gives nitrobenzene plus H positive removed by a base. Third, nucleophilic substitution reactions. Substitution reactions of alkyl halides are nucleophilic substitution reactions. OH negative plus CH3I gives CH3OH plus I negative methanol. 3.10.2 Addition reactions. An addition reaction involves the combination between the molecules of two reacting substances to form a single compound known as the addition product. One of the reactants in such reactions always contains double or triple bond in its molecule. For example, CH2 double bond CH2 ethylene plus Br2 gives BrCH2 CH2 Br ethylene dibromide. Addition reactions may also involve free radical electrophilic or nucleophilic reagents, as they are subdivided as: first, free radical addition reaction. Addition of HBr to alkenes in the presence of benzoyl peroxide is a well-known example of free radical addition. CH3CH double bond CH2 plus HBr benzoyl peroxide gives CH3CH2 CH2Br and propyl bromide. Second, electrophilic addition reactions. Most of the addition reactions of alkenes are electrophilic addition reactions. CH3CH double bond CH2 plus HX gives CH3CH positive CH3 plus X negative. CH3CH positive CH3 plus X negative gives CH3CHX CH3 isopropyl halide. 3. Nucleophilic addition reactions. Aldehydes and ketones undergoes nucleophilic addition reactions. CH3CH double bond O acetaldehyde plus Cn negative gives CH3CHO negative Cn, and then H positive CH3CHOHC and acetaldehyde cyanohydrine. 3.10.3 Elimination reaction. This reaction involves the loss of atoms or group of atoms from a molecule to form compounds containing double or triple bonds. Thus, these reactions are essentially the reverse of addition reactions. The common reactions of this type involves the elimination of atoms or groups from adjacent carbon atoms to yield alkenes. For example, CH3CH2CH2Cl Propyl chloride plus KOH alcohol gives CH3CH double bond CH2 propylene plus KCl plus H2O. Elimination reactions are further divided into two types as given below. First, unimolecular elimination E1 reaction. These are elimination reactions in which rate determining step involves only one molecule. For example, dehydrogenation of tertiary alkyl halides usually proceeds by E1 mechanism. CH3C, CH3, CH3Cl, tert-butyl chloride plus KOH alcoholic. CH3C, CH3 double bond CH2 plus KCl plus H2O. Second, bimolecular elimination E2 reactions. These are elimination reactions in which rate determining step involves two molecules. For example, primarily alkyl halide such as N-propyl chloride shown above generally undergo dehydrohalogenation of E2 mechanism. Depending upon the relative position of atoms or group eliminated, these reactions are also classified as alpha, beta and gamma elimination reactions. First, alpha elimination reactions. These are reactions in which loss of two atoms or group occurs from the same atom of a substituent. For example, CCl3H chloroform plus OH negative gives CCl2 dichlorocarbene plus H2O plus Cl negative. Second, beta elimination reactions. In this reaction, loss of two atoms or group occurs from adjacent atoms of a substance. For example, CH3CH2OH ethanol in presence of concentrated H2SO4 FCH2 double bond CH2 ethene plus H2O. Third, gamma elimination reaction. In this reaction, loss of two atoms or group occurs from alpha and gamma position of a molecules, giving rise to the formation of three-membered ring CHBr, CH2, CH2Br, CH2, CH2Br, 1,3-dibromopropene in presence of zinc dust. Freud reaction gives CH2, CH2, CH2 cyclopropane plus Zn Br2. 3.10.4 Rearrangement reactions. These reactions involves either the migration of a functional group from one atom to the other or the incomplete rearrangement of the chain of carbon atoms present in the compound to form a new product. For example, CH3, CH2, CH2, CH2Br, 1-bromobutane gives in presence of AlCl3 and 575 Kelvin gives CH3, CH2, CHBr, CH3, 2-bromobutane. CH3, CH2, CH2, CH3 and butane in presence of AlCl3 HCl. Heat is in sealed tube gives CH3, CH, CH3, CH3, 2-methyl propane. This rearrangement also takes place through the formation of electrophilic, nucleophilic or free radical intermediates. It is interesting to note that the preparation of first organic compounds, that is urea, to be synthesized in the laboratory involves a rearrangement reactions. Ammonium cyanate NH4CNO gives heat NH2CO NH2 urea. 3.10.5 Isomerization reactions. This reaction involves the conversion of one isomer into another so that the molecular formula and the carbon skeleton of the reactants and the product always remain the same. For example, conversion of trans 2-butene to cis 2-butene and vice versa is a geometrical isomerization reaction. CH3 CH double bond CH CH3 trans 2-butene in presence of heat gives CH3 CH double bond CH CH3 cis 2-butene. 3.10.6 Condensation reactions. These are reactions in which two or more molecules of the same or different reactants combine to form products with or without the elimination of a simple molecule such as water or alcohol. For example, when acetaldehyde is treated with a dilute alkyl, two molecules of acetic aldehyde combine to form 3-hydroxybutanol. The reaction is known as aldol condensation. CH3COH plus CH3CHO acetaldehyde, two molecules gives in presence of dilute NaOH gives CH3CHOH CH2CHO 3-hydroxybutanol or aldol. 3.10.7 Molecular reactions. These are reactions which involves a reorigination of covalent bonds either intramolecularly or intermolecularly through cyclic transition states under the influence of heat or light. These reactions do not require any catalyst or non-ionic or free radical intermediates is involved. These are collectively called pericyclic reactions. Electrocyclic and cycloaddition reactions are typically examples of such reactions. First, electrocyclic reactions. These reactions involves conversion of an alkyl diene to a cyclic alkene and vice versa. For example, put 1,3-diene in presence of heat gives cyclic transition state, then gives cyclic butene. Second, cycloaddition reaction. This reaction involves addition of two unsaturated molecules of the same or different substance to form cyclic products. An example of this type is 4 plus 2 cycloaddition reaction given below. The student which come across the detailed mechanism of various reactions at appropriate place is in the text. 3.11 Energy changes during reaction. All chemical reactions involves the breaking and making of bonds. Since energy is required to break a bond while energy is released in the formation of a bond, the occurrence of chemical reaction is always accompanied by energy changes in one form to the other. We will therefore now present briefly certain basic concepts regarding energy changes such as enthalpy of reaction, energy of activation and transition state. 3.11.1 Heat or enthalpy of reaction. Heat or enthalpy of reaction delta H is the total energy change which accompanies the conversion of a definite number of molecules as required by the balanced equation of the reactant in the products. It is possible to calculate the enthalpy of a reaction on the basis of bond dissociation energy of various bonds broken and formed during the reaction. For instance, let us consider the following hypothetical reaction. AB x1 plus CD x2 gives AC x3 plus BD x4. Let us suppose that x1, x2, x3 and x4 represent the bond dissociation energy of the respective bonds involved in the reaction. During the reaction, two bonds A, B and CD are broken while the two new bonds AC and BD are formed. The two bonds broken require a total of x1 and x2 kilojoule per mole of energy, while the two bonds formed liberate a total of x3 plus x4 kilojoule per mole of energy. Therefore, the total energy change during the reaction, or in other words, heat of the reaction, should be x1 plus x2 minus x3 plus x4. It is apparent that if the energy consumed, that is x1 plus x2, is more than that the energy released, that is x3 plus x4, there would be overall consumptions of energy, that is the reaction would be endothermic and delta H would have a positive value. On the other hand, if energy consumed x1 plus x2 is less than the energy released x3 plus x4, there would be a net liberation of energy, that is the reaction would be exothermic and delta H would have a negative value. Thus, the reaction between methane and chlorine, CH3 H 433 kilojoule plus ClCl 242.5 kilojoule gives CH3Cl 350 kilojoule plus HCl 430 kilojoule. Delta H is equal to 433 plus 242.5 minus 350 plus 430 equal to minus 104.5 kilojoule. Is an exothermic reaction since it results in the depletion of a 104.5 kilojoule of energy for every mole of methane converting into methyl chloride. On the other hand, the reaction between methane and iodine is an endothermic reaction. CH3H433 kilojoule plus II151 kilojoule gives CH3I 234 kilojoule plus HI 297 kilojoule. Delta H is equal to 433 plus 151 minus 234 plus 297 is equal to 53 kilojoule. 3.11.2 Energy of activation theory. Collision theory. An important feature of most of the reaction, whether endothermic or exothermic, is that the reactants required some extra energy for the reactions to take place. To understand the reason for this, let us recall that according to collision theory of reactions, the primary conditions of a reactions to take place is that the reacting particles must come in contact or collide with each other, but all the reactions or collision should fulfill two conditions. First, the colliding particles must have a certain minimum amount of energy known as threshold energy. Second, the colliding particles must be properly oriented with respect to each other at the time of collision. As far as the energy factor is concerned, most of the reactant molecules do not possess sufficient energy in their ground state for effective collisions to take place. As a result, when such molecules collide with each other, no bond breaking or making takes place and the colliding particles bounce back as such. Therefore, extra energy is needed by the reactants to form the product. The minimum amount of addition energy required by the reactant to undergo effective collision is known as activation energy, EA. It is numerically equal to the difference between threshold and the ground state energy of the reactants, that is, E act is equal to E threshold minus E ground state. Most of the organic reactions have activation energy in the range of 40 to 150 kilojoule per mole. If the activation energy has a low value, the reactions can take place even at room temperature. On the other hand, reactions with the high activation energy take place only on heat. Energy barrier to the reactions. The concept of activation energy means that the reactions have to be activated or raised to a higher energy level before they form the products. In other words, there exists a certain energy barrier between the reactants and the products. And depicting the progress of a reaction, this barrier is generally represented as an energy hump, which has to be surmounted before the reaction can be completed. Figure 3.1. It may be compared to a pass on the top of a hill separating two valleys on the two sides of the hill. To move from one valley to the other, one must move up to the hill and cross the pass. Similarly, the reactants must move up to the energy level and cross the energy barrier or hump to yield the product. A graphical representation of activation energy and energy barrier. It is interesting to note that even though a chemical reaction involves breaking and making of bonds, the two processes are not perfectly synchronized. At the same time, the energy released through bond formation is not completely available for bond fusion. This also explains why the reactants required extra energy for the reactions to take place. 3.11.3 Gives free energy changes. Gives free energy changes delta G is a very useful parameter for determining the feasibility and direction of occurrence of a reaction. It is related to the change of enthalpy delta H and change in entropy delta S as follows. Delta G is equal to delta H minus T delta S. When all the substances are in their standard state, the relationship may be written as delta G naught is equal to delta H naught minus T delta S naught. The enthalpy term delta H naught is directly related to the bond strength in the starting substance and the product. The entropy term delta S naught is a measure of the change in the amount of molecular randomness or disorder caused by the reaction. A reaction takes place in the forward direction only if it has a negative value of delta H, that is free energy of the product is less than that of a reactant. On the other hand, a positive value of a delta H means that the reaction has a tendency to take place in the backward directions. In case of equilibrium reaction, the equilibrium constant K is related to delta G naught, as delta G naught is equal to minus 2.303 RT log K. Three point 11.4 Transition state theory. Energy diagram of a reaction. So the transition state theory has been very useful in understanding the mechanism of organic reactions and the energy changes takes place during the reaction. According to this theory, the reactants do not change directly to the product, but what happens is that when the reactants molecules come in contact with each other, it leads to the formation of a highly unstable arrangement of atoms whose energy corresponds to the energy barrier separating the reactants and the products. The high energy species thus formed is known as activated state or transition state. For example, in a single step reaction represented by the equation A plus B A plus B C gives AB plus C. The high energy transition state may be presented as ABC. The dotted lines indicate partial bonds. The transition state merely represents a probably arrangements of atoms corresponding to the energy barrier in which a bond is partially but not completely broken and a new bond has begun to form but is not yet completely formed. It does not represent a substance which can be isolated or even detected. As soon as this transition state is formed, it splits into the products. Thus, the complete reaction sequence may be represented as A plus BC reactants gives ABC transition states, then gives AB product plus C. The free energy difference between the reactants and the transition state is known as free energy of activation, denoted as delta G. Positive, it determines the rate at which reactants reaches the transition state, which in turn determines the rate of reaction. A small value of delta G positive means that there is a only small difference in energy between the reactants and transition state, and therefore the reaction which take place rapidly. Conversely, a large value of delta G positive means the reaction would take place slowly. The transition state is in equilibrium, which reactants and its concentration is determined by the equilibrium constant K++, which is related to the free energy of activation as delta G positive gives delta H positive minus T delta S positive is equal to minus 2.303 RT log K positive, where delta H positive is the enthalpy of activation and delta S positive is the entropy of activation. Note the superscript positive known as double dagger is always used when referring to activation parameters involving the transition state. Figure 2.3 shows the free energy of reactants transition states and products. Free energy of activation delta G double dagger involves in the formation of a transition state, and the net free energy changes delta G not for a single step reaction. Such a diagram, which shows the energy of various species and the energy changes takes place during the progress of a reaction from beginning to end, is known as energy profile or energy diagram of the reaction. It is to be noted that the reaction energy diagrams of all reactions are not similar to figure 3.2. On the other hand, each reaction has its own specific energy diagram depending upon the value of delta G double dagger and delta G not energy diagram for a single step reaction. 3.11.5 Energy diagrams for multi-step reactions. Reactions can proceed from a reactant to product either directly in a single step known as concentrated reactions, or in any take place through two or more steps, which include the formation of one or more intermediates, since the reaction is directly converted into the products without the formation of any intermediate substance. In the concerted reactions, the energy diagram of such reactions have only two energy minima corresponding to the reactants and the products, and an energy maximum corresponding to the transition state as shown in the figure 3.2. Most of the reactions of organic compounds are multi-step reactions involving the formation of one or more reactant intermediates. Therefore, let us now consider the complete energy diagrams of multi-step reactions. Therefore, let us now consider the complete energy diagram of multi-step reactions with the help of two-step reactions involving one reaction intermediates. Reactants gives transition state 1, reactive intermediates step 1, reactive intermediates transition state second, products step 2. In such reactions, we draw an energy diagram for each of the individual steps and then join them in the middle as the product of step 1, that is reactive intermediates act as the starting material for step 2, figure 3.4 and 3.5. Since the intermediates have higher energy than either the reactants or products, it is a very reactive and may or may not be isolated. However, unlike the transition state, the intermediates has a measurable lifetime. Depending upon the free energies of activation of the two transition state, the free energy diagrams can be of two types as shown below. First, if the free energy of activation of transition state 1 is more than the transition state 2, the energy diagram is as shown in figure 3.3. In such cases, the intermediates readily get converted into the product and can be seldom isolated. The first step of such reactions is the rate determining step of the overall reaction. Figure 3.3 Energy profile for a two-step reactions in which the first step is rate determining step. Figure 3.4 Energy profile for a two-step reactions in which the second step is the rate determining step. Second, if the free radical of activation of state 2 is more than the transition state 1, the energy diagram is shown in figure 3.4. In such cases, the intermediates are rather stable and can be isolated. The second step of such reactions constitute the rate determining step of the overall reaction. It may be pointed out that for the many reactions which we study, the enthalpy changes which takes place during the reactions are much larger and more important than entropy changes. Therefore, it is sometimes found convenient to ignore the entropy changes in such reactions. As a result, the reaction energy diagrams may be drawn in terms of the energy of activation EA in place of free energy of activation delta G double dagger. Similarly, the energy changes takes place during the reactions may be depicted in terms of delta H naught instead of delta G naught. It may be reminded, however, that in A is very closely related to uh, delta G double dagger, and delta H naught is very nearly equal to delta G naught. Figure 3.5 shows the energy diagrams of an exothermic reaction in terms of EA, while figure 3.6 shows the energy diagram of an endothermic reaction. Figure 3.5 energy diagram of an exothermic reaction. Figure 3.6 energy diagram of an endothermic reaction. It may be noted from this diagram that first, the difference in energy level between the reactants and the transition state represent the E act. The difference in energy level between the reactants and the products represent the delta H. Second, for an endothermic reaction, E act must be at least as large as delta H, although generally it is larger. Third, for an exothermic reaction, E act may be high or low. Generally, it is on the lower side. 3.11.6 Development and structure of transition state. Hammond postulates in order to fully understand reaction, it is necessary to complete understand the structure of and energy of the transition state, which leads to the formation of product. But the transition state has only a transitory existence. As soon as it is formed during the course of a reaction, it changes into a more stable species, but it is possible to have an idea of the structure of a particular transition state from the reaction energy diagram with the help of Hammond postulates. 1955 advanced a generalization known as Hammond postulates to correlate the energy and structures of transition state. According to this postulate, the structure of the transition state most closely resembles the structure of the stable species that lies closest to it in energy. For example, in a strongly endothermic reaction, the energy level of the transition state is much closer to that of the product that reactants. Therefore, the transition state would be accepted to closely resemble the products in structures as well. On the other hand, in a strongly exothermic reaction, the transition state is energetically most closer to the reactants than the products. As a result, it has a strong resemblance to the reactant structurally. For a two-step reactions, the first transition state may structurally resembles either the original reactants or the intermediates, whichever is closer to it in energy. The second transition state in turn may resemble structurally either the intermediates or the final products, according as which the energetically closer to it. 3.11.7 Effect of a catalyst on the transition state. Many reactants which we shall study involves the use of some suitable catalyst to increase the rate of reaction. What the catalyst does in such reactions is to provide an alternate path from reactant to product with a lower energy transition state. Thus, the catalyst lowers the energy of activation required for the reaction so that the rate of reaction increases. It must be pointed out, however, that the delta H or delta G for the reactions remains unchanged even in the presence of catalyst. 3.12 Assigning formal charges on intermediates and other ionic species. While studying the various reaction intermediates, it has found that these species may either carry positive or negative charges, or they may be neutral in character. In order to predict whether a given species carries some charges or not, we now present a very simple method known as formal charge method. For charge explanation on intermediates, formal charge, it is the amount of positive or negative charge which can be assigned to certain atoms of a species in order to know whether the species has a whole carries some charge or not. The calculation of formal charge involves the comparison of the number of valence electrons in a neutral atom in the free state and the number of valence electrons associated with the atoms in the bonded state. The difference between the two values gives the formal charge on an atom in a given species. That is, formal charge on an atom in a given species is equal to the number of valence electrons in the free atom minus number of valence electron in a bonded atom. Calculation of a number of valence electrons in the bonded state. To calculate the number of valence electrons associated with an atom in the bonded state, first, the number of electrons shared between two atoms are divided equally between the two atoms that share them. This means that even though the electrons are shared between the two atoms, it is still though as if each atom owns one electron of the shared pair. Second, the number of non-bonding valence electrons of an atom are assigned exclusively to that atom. The sum of the number of electrons assigned as above gives the number of valence electrons in the bonded state. This is also sometimes referred to as the average electrons, that is, number of electrons in the bonded state or average electrons is equal to 1 by 2 into number of shared electrons plus number of non-bonded electrons. Therefore, the formal charge on a bonded atom may also be expressed as a formal charge on an atom is equal to number of valence electrons in the free atom minus half into number of shared electrons plus number of non-bonded electrons. Formal charge on the species as a whole. Knowing the formal charge on each atom in a given species, the formal charges on the species as a whole can be found by adding together the formal charges on various atoms. That is, formal charge on a species is equal to sum total of formal charges on all the atoms in a given species. We now illustrate the complete procedure by considering the example of the simplest molecule, methane, CH4. It is apparent from this structure that carbon is surrounded by 8 electrons which are shared with 4 hydrogen atoms. Therefore, the number of valence electrons associated with carbon in methane is 1 by 2 into 8 is equal to 4. Since the number of electrons in a free carbon atom is also 4, the methane carbon is electrically neutral. In other words, there is no formal charge on carbon atom in methane. We can also arrive at the same conclusion directly. Formal charge on carbon is equal to number of valence electron in a free atom minus half number of shared electrons plus number of non-bonded electrons is equal to 4 minus half into 8 plus 0 is equal to 4 minus 4 is equal to 0. Each hydrogen atom in methane is surrounded by 2 electrons which are shared with carbon. Therefore, formal charge on each hydrogen is equal to 1 minus half into 2 plus 0 is equal to 0. That is, formal charges on methane molecules is equal to formal charges on carbon plus 4 into formal charges on each hydrogen is equal to 0 plus 4 into 0 is equal to 0. It is of course well known that methane molecules has no net electrical charges. Let us now compute the formal charges on some of the intermediates already studied. First, free radicals. It has been stated earlier that free radicals are electrically neutral species. To justify this, let us consider the methyl radical CH3 dot, which is the simplest free radical. The carbon is surrounded by 6 bonded electrons shared with 3 hydrogens and 1 non-bonded electrons. Each hydrogen is surrounded by 1 2 unshared electrons. Therefore, formal charge on carbon is equal to 4 minus half into 6 plus 1 is equal to 0. Formal charge on each hydrogen is equal to 1 minus half into 2 plus 0 is equal to 0. Formal charge on methyl radical is equal to formal charge on carbon plus formal charge on hydrogen is equal to 0 plus 3 into 0 is equal to 0. Second, carbocations. The positive charge on the carbocations may be verified by considering the case of a methyl carbocation, CH3 positive. It may be easily seen that formal charge on carbon is equal to 4 minus half into 6 plus 0 is equal to plus 1. Formal charge on each hydrogen is equal to 2 minus half into 2 is equal to 0. Formal charge on the carbocation is equal to plus 1 plus 3 into 0 is equal to plus 1. Third, carbon ions. It is well known that carbon ions are negatively charged species in which a carbon atoms carries negative charge. To rationalize this, we may consider the structure of a methyl carbon ion. CH3 negative. Formal charge on carbon is equal to 4 minus half into 6 plus 2 is equal to minus 1. Formal charge on each hydrogen is equal to 1 minus half into 2 plus 0 is equal to 0. Formal charge on carbon anion is equal to minus 1 plus 3 into 0 is equal to minus 1. Fourth, carbenes. The simplest carbenes in methylene CH2. The formal charge on carbon is equal to 4 minus half into 4 plus 2 is equal to 0. Formal charge on each hydrogen is equal to 1 minus half into 2 is equal to 0. Formal charge on carbene 0 plus 2 into 0 is equal to 0. Carbenes are neutral species. Fifth, nitrines. The neutral character of nitrines may be verified with the formal charge calculation on methyl nitrine. CH3N. Formal charge on carbon is equal to 4 minus half into 8 plus 0 is equal to 0. Formal charge on nitrogen is equal to 5 minus half into 2 plus 4 is equal to 0. Formal charge on each hydrogen is equal to 1 minus half into 2 is equal to 0. That is, formal charge on nitrogen is equal to formal charge on carbon plus formal charge on nitrogen plus 3 into formal charge on hydrogen is equal to 0 plus 0 plus 3 into 0 is equal to 0. Problem 3.4. Calculation the formal charges on each atom and verify the total charge carried by the molecule or ion for each of the following species. First, NH4 positive, second NH2, third CO2, fourth BF4 negative. First, N is equal to plus 1, H is equal to 0, then NH4 positive is equal to plus 1. Second, N is equal to minus 1, H is equal to 0, then NH2 negative is equal to minus 1. Third, C is equal to 0, O is equal to 0, then CO2 is equal to 0. Fourth, B is equal to minus 1, F is equal to 0, BF4 is equal to minus 1. Thank you.